For the longest time, black holes were just these monsters lurking in the math of general relativity. But now we're actually starting to see them. So today, we're going to take a journey right from the very edge of what we can observe, all the way to the deepest, most mind-bending theories about what's really going on inside, or if there even is an inside at all. And we're starting right here, at the heart of our very own Milky Way. This is Sagittarius A star, our supermassive black hole, seen for the very first time in polarized light. But this isn't just another pretty picture from the Event Horizon Telescope. Nope. What they've given us is a map of the invisible, powerful forces that are shaping the very edge of reality itself. All right, so for the first part of our trip, we're going to explore what we can actually see, what we can measure, right at that brink, right at the point of no return. So how in the world did they make a map of invisible forces? Well, they used something called polarized light. It actually works a lot like a pair of polarized sunglasses. You know how they cut down on glare? They do that by filtering out light waves that are all jiggling in the same direction. Well, astronomers can do the same thing, but on a cosmic scale. See, the super hot gas swirling around the black hole gives off light, and that light gets polarized by the magnetic fields. So if you can map that polarization, boom, you get a direct look at the structure of those magnetic fields. And this right here, this is the crucial point. The team found that these magnetic fields aren't just some chaotic, tangled mess. As Sarah Asaun, one of the project leads, said, they are strong, twisted, and organized. They're spiraling around the black hole's edge, almost like water swirling down a drain. And here's where it gets really, really fascinating. Over on the right, that's M87 star, the first black hole we ever got a picture of. It's an absolute behemoth. On the left is our own Sagittarius A star, which is way, way smaller. But look at them. Even though M87 star is literally thousands of times more massive, their magnetic field structures are, well, they're strikingly similar. This is a huge hint that maybe these powerful organized fields are a fundamental blueprint for all supermassive black holes. And that similarity, it has a massive implication. We already know that the magnetic fields around that monster, M87 star, are strong enough to launch these colossal jets of material out into space at nearly the speed of light. So seeing the exact same kind of structure around our black hole, it suggests that Sagittarius A star might be able to launch a powerful jet too, one that's maybe just hidden from our current view. Okay, so we can map the forces at the very edge. That's incredible. But that just opens up the door to an even deeper mystery. How on earth can we probe what's happening inside? I mean, this has always been the fundamental problem, right? The event horizon is a one-way street. Information goes in, but it can never, ever come back out. So how could we ever hope to map the interior? But get this, an absolutely astonishing new line of thinking suggests we might not have to cross the horizon after all. Some physicists are now proposing that the information about what's inside isn't truly lost. Instead, it's encoded on the outside. And we might just be able to use that information to reconstruct the geometry inside. Think of it like a cosmic CT scan. Basically, physicists have found this incredibly deep mathematical connection between what happens outside the black hole and what happens inside. So by carefully measuring certain properties of spacetime in the exterior region, stuff we can actually theoretically observe, they believe they can use this newfound connection to mathematically solve for the geometry of the interior. It's a way to map the unseeable. And the takeaway from this is just mind-bending. The inside and the outside are not totally separate realities. They are deeply fundamentally entangled. This new work suggests that connection is so strong, it could actually let us map the inside just by looking very, very carefully at the outside. So if we can theoretically peek inside, what do these new methods actually show us? Well, the answer, in one word, is chaos. Let's dive into the bizarre and dynamic universe that might be hiding inside the event horizon. You know, the old, simple picture of a black hole interior is getting thrown out the window. Recent studies show that for some black holes, that stable inner horizon we expected to find, well, it's just not there. In its place, you get a series of evolving, dynamic, chaotic regimes. It's like a whole universe of chaos deep inside. Now, to try and make sense of all this chaos, physicists use a tool called the Kasner exponent. You can think of it as a kind of dial that measures just how violently spacetime is being twisted and distorted deep inside the black hole. Stretching like crazy in one direction while being crushed in another.
And just look at what that exponent is doing in this visualization. This is not a smooth, gentle collapse into a single point. This graph shows that the Cosner exponent is oscillating wildly. That means space-time itself is being stretched and squeezed, whipping back and forth with incredible violence the deeper and deeper you go.
But here's the most amazing part. All this chaos, it isn't random. Turns out it has a deep, predictable mathematical structure to it. It's so predictable, in fact, that scientists can actually tune it in their models. So what does that mean? It means the black hole's interior isn't just a dead end. It's a dynamic, complex, and maybe even an understandable system. Okay, so far we've been running with the assumption that there is an interior. But for our final section, we're going to explore the most radical, most out there idea of all. What if there isn't?
For 100 years, this has been the end of the story, right? General relativity tells us that at the heart of every single black hole, there is a singularity.
A point of zero size and infinite density, a place where our equations just stop making any sense, where gravity goes to infinity, and the laws of physics as we know them, they just completely collapse. And for decades, physicists have looked at that and thought, okay, that's a sign our theory is broken. But a brand new proposal is asking a truly breathtaking question. What if the problem isn't that our theories break down inside the black hole? What if the interior simply never forms in the first place? The idea is called the waffled, and it's wild. It proposes that when space-time gets curved to a certain critical limit, three-dimensional space doesn't collapse down to an infinitely dense point. Instead, it goes through a transition, and it gets compressed into a finite, two-dimensional surface. And beyond that surface, there's nothing. Space-time itself just stops. It's a literal edge of reality. As the author of the idea, Javier Viana, puts it, the boundary is all that remains of space-time. So in this model, all the information that falls into the black hole isn't crushed into some unknowable singularity, it's actually encoded onto this final two-dimensional surface. Let's just put these two ideas side by side, because the difference is huge. A singularity is an infinitely dense point where physics breaks. The warfold is a finite surface where space-time just ends. A singularity hides this mysterious interior region, but the warfold says that interior never even forms. It's a radical idea, for sure, but maybe, just maybe, an elegant solution to one of the biggest problems in physics. Our entire picture of black holes is being redrawn before our very eyes, from those spiraling fields at the edge to the chaotic reality that might lie within, to even the possibility that there's no within at all. And it leaves us with this one profound final question. Are black holes a gateway to a hidden universe, or are they the ultimate wall at the very edge of existence? The journey to find out has really only just begun.